Now, continuing on in section 3.4, we want to find the solutions of this inequality. First thing I'm going to do is double check, is my left side as simple as I can get it? Yep, I just have a 15. But my right side is not. I can get rid of my parentheses first by distributing. I'm going to take the negative 2 in to each of these pieces. It's going to give me a negative 8m minus 14. Negative 2 times 4m and negative 2 times 7. I'm going to bring everything else down. 15 is less than or equal to 5, and then minus 8m minus 14. My right side is still not as simple as I can get it because I have like terms here. 5 minus 14 gives me negative 9. I still have that minus 8m, and my inequality relationship didn't change with my 15 there. Both sides are as simple as I can get them now. Both expressions are simplified, so I can solve. It's being multiplied by negative 8 and subtracted by 9. I get rid of subtraction by adding, and whatever I do to one side, I have to do to both. Here I get 24. Negative 9 plus 9 is 0, so I'm left with the negative 8m. Don't forget to take the sign with your number there. M is being multiplied by negative 8. I get rid of it by dividing. I get negative 3. Negative 8 divided by negative 8 is 1 times m is m. And because I divided by a negative number here, I have to flip my inequality. So I get negative 3 is greater than or equal to m. Here I plugged in negative 3, set it equal to my original value. Both expressions equal to each other, got a true statement, so my boundary point is right. Then I picked a number that makes my solution true, so I picked negative 4 here and substituted that in. Negative 3 is greater than or equal to negative 4. And when I got to the bottom here, I got 15 is less than or equal to 23, which is true, so my solution is correct. In example 4, we want to find our solutions here. Our left expression is as simple as we can get it, and so is our right expression, but I have variables on both sides. When we were solving equations, we liked to move the smaller one because then we had less negatives, and the same is true here. With inequalities, though, it's extra important that we don't have negatives. Not that we can't deal with them, but it's one less thing to forget by flipping that inequality. So 6 and 3 is smaller, that's the one I'm going to move. And again, whenever we move from one side to the other, we have to do the opposite. Right now I have a positive 3, so I'm going to subtract a 3n. And again, that's like terms with my 6n, so those can go together. What I get here is 3n. 3n minus 3n is 0. I did not change my constant terms at all. Okay, I moved my variables together. They were like terms, so those changed, but my constant terms did not. Now I have variables all together on one side. I need my number parts on the other. I'm going to go ahead and solve. N is being multiplied and subtracted, so we get rid of our subtraction first by adding. Whatever I do to one side, I do to both. N is being multiplied by 3, so we get rid of it by dividing. Here I get n and 3, and because I chose to have a positive coefficient, I can bring my inequality symbol right down. And I get n is greater than 3. If we'd have moved and subtracted the 6, we'd have had a negative 3 to divide by, and we'd have had to flip our inequality. We get to the same spot, it's just one more thing to have to remember. Here I checked both 3, our boundary point, and 4, a number that makes this true. 4 is greater than 3. Both of them gave me true statements, so we are correct. Feel free to pause here and give this a try. My left expression is as simple as I can get it, and so is my right expression. But I have b's in 2 spots here, so I'm going to try and get those together. I have a 3b and a negative 2b. Negative 2 is smaller, so I'm going to move my smaller one here. To get rid of subtraction, I add. Whatever I do to one side, I do to both. Negative 2 plus 2 gives me 0 b's on that side, on my right side, which is perfect. On my left side, I have 5 b's. Notice how I did not change my constant terms. My 12 and my 27 did not change. The only thing that changed were my variables. Now I can solve. B is being multiplied by 5 and added by 12, so we get rid of our addition first by subtracting. Whatever I do to one side, I have to do to both. I get 5B, 12 minus 12 is 0, is greater than 15. B is being multiplied by 5, so we divide by 5. And we get 3. Now, again, remember, anytime we multiply or divide, we have to check, do we multiply or divide by a negative number? Here it was positive, so we get to keep our inequality symbol. If we'd have moved our 3 over and had a negative 5, then we'd have had to flip it. So keep that in mind. If we always move the smaller of our two variable terms here, then that's one less thing we have to worry about by remembering to flip that inequality. Here I checked both our boundary point equal and got an equivalent statement, equivalent equation there, and I checked a number that makes our inequality solution true, like 4. 4 is greater than 3. So I plugged 4 into both spots and also got an equivalent or a true statement with my final inequality there. So our answer is correct. Just like with equations, sometimes when we solve an inequality, we get a statement that is always true. That gives us a solution of all real numbers. Similarly, though, sometimes solving an inequality gives us a statement that is never true, which gives us no solution. This can look a little bit different, though, guys. For an always true, with equations, we got something like 4 equals 4. Here we could get something like 4 is greater than negative 2. That's always true, okay? Never true could be something like 3 is less than negative 10. Is 3 less than negative 10? Never. Okay, also we have to be careful about our equals part of it. If we get something like 10 is less than 10, that is not true. It would have to have the equals for that to work. So be careful there. Think about these really closely to determine whether or not they're true or false. In example 5, we want to find the solutions. My left expression is as simple as we can get it, but my right one is not. So I'm going to go ahead and distribute to get rid of those parentheses. 2 times 5 is 10, and 2 times negative 4a is negative 8a. Again, I didn't change my left expression here at all, and I didn't change my inequality. Now, I have variables on both sides, so I'm going to go ahead and get those together by adding 8a. And when I do that, negative 8 plus 8 is 0. And negative 8 plus 8 is 0. So all I have left then is 10 is greater than or equal to 10. That is a true statement. 10, it's not greater than 10, but it is equal to, and it's greater or equal to. So, since that is a true statement here, our solution is going to be all real numbers. Anything that we plug in there is going to give us a true statement. Our symbol for that looks like this. You can either write it out or you can use our symbol there, which is, again, it's an R with 2 lines through it. On B, my left expression is as simple as I can get it, 6m minus 5. My right side is not. I have like terms. 7m minus 1m gives me 6m. I still have a plus 7, and my left side didn't change at all. Now, I'm going to get my variables together on one side, since I have them on both sides, by subtracting 6m. 6 minus 6 is 0, and 6 minus 6 is 0. Those variable terms are completely gone. What I'm left with is negative 5 is greater than 7, which is false. Negative 5 is not greater than negative 7. So here, my answer is no solution. And again, remember our symbol for that is this, null set, empty set, no solution. Now, feel free to pause here and give this a try if you'd like. For A, both expressions are as simple as we can get them. So I'm going to go ahead and try and get my variables together on one side. I get rid of a 5 by subtracting. Positive 5 to get to 0, we take it away. 5 minus 5 gives me 0. and 5 minus 5 give me 0. I have no n's left. What I do have left is 9 less than or equal to negative 1. 9 is not less than or equal to negative 1, so this is false, which means we have no solution. You can also use our symbol. No number that we could find to plug in there is going to make that a true statement. Try and give B a try here. My left expression is as simple as we can get it, but on my right side it is not. I have 7x minus 1x, which gives me 6x when I combine my like terms. I didn't change anything on my left side, and I still have the plus 2 here on my right side. Now I have variables on both sides, so to get my x's together, I'm going to subtract a 6x. Because 6 minus 6 gives me 0, so I have no x's left on that side. It also happens to give me 0 on my right side. So what I have left is 8 is greater than or equal to 2. That checks, that's true. So because it's true, our solution is all real numbers. Any number that you can think of, if you plugged it in there, would give us a true statement. And again, we can also use that symbol if you'd like. Quick recap here. In the same way multi-step equations are solved using properties of equality, multi-step inequalities are solved using properties of inequalities. The properties of inequality are used to transform the original inequality into a series of simpler equivalent inequalities. And that's all I have for section 3.4.